This is the problem where we need to establish the formula for tangent line and normal plane for the curve defined in three-dimensional space. So first of all, I'm going to define the function, which is the vector function. It takes the scalar value from the field of real numbers and reflects that to the vector space. So basically this is for any scalar value from our real numbers field, there exists some sort of vector which belongs to a three-dimensional space, such as vector equals f of t, right? And I'm going to designate this vector as x, y, and z, and this is the x of t, y of t. So each value, each coordinate is individual scalar function taken with respect to the scalar value r. So each x is essentially the function from r to r, and then the same for y is the function from r to r, and z is the function from r to r scalar functions. We know that by definition, the derivative of this vector function is exactly the derivatives of each of these coordinate functions, d of y with respect to t, and d of z with respect to t as well. So this is the vector function. So the direction of this vector function is, as we know it, collinear to tangent line. So all we need to do to find the tangent line to take this derivative of this radius vector, multiply it by the parameter, and add to the initial point. Let's suppose we have initial point on a graph. Let's call it x0, y0, and z0. Then for our line, we have x0 plus some parameter value multiplied by the coordinate of this radius vector derivative, which is dx of dt. And we know that this derivative should be taken at t0 because this is the exact point where we need to find this derivative. If we take a look at the graph, this is going to be something like this. This is the radius vector at the specific point t0, right? This is the radius vector. This is the radius vector derivative at the specific point t0, and then we're multiplying it by some sort of scalar value. Scalar value returns like its multiple, it's something bigger, and then we add this multiple to the initial point. This one is initial point, let's call it p, and adding the vector, the multiple of this tangent vector will give us the tangent line, the coordinates, the arbitrary coordinate in the tangent line. And this is going to be the tangent line, the whole tangent line. So that's pretty simple. So y is the y0 plus s parameter times dy dt t0, and z is z0 plus s, the same as dz dz t0, so on. And then we can even kind of extract the parameter s here. Parameter s would be x minus x0 over dx dt at the point ty, which is equals to y minus y0 dy dt, which equals z minus z0 dz d over t, and at specific t0, of course. So that's pretty much it for the tangent line. Now how to find the normal plane. For normal plane, we know that this normal plane would be perpendicular. Normal plane would be perpendicular with the orthogonal to tangent line. Which is equivalent to saying that for any vector, let's call it v, which lies in this normal plane, this vector would be perpendicular to tangent line. This is just one of the main axioms of stereometry, or whatever it is called. And so for the vector v, we can represent this vector and define it as x, which is arbitrary point on our plane, minus x0, y minus y0, z minus z0, and the tangent line, as we find that tangent vector, can be defined as dr dt at t0, sorry, dr dx, then dy dt at t0, and dz dt at t0. So we know that this is perpendicular, that's its inner product equals 0. Consequently, x minus x0 times dx dt plus y minus y0 dy over dt plus z minus z0 times dz over dt equals 0 at a specific t0 belonging to scalar field. So that's pretty much it. These are two formulas for both the tangent line and, as you can see, for the normal plane.